Howdy, this is Mr. Potter. Today we're going to go through day 1 of section 3.7. What we've been dealing with so far are derivatives of functions. And so what we want to start talking about is how do we deal with relationships that aren't functions. And we have a tool called Implicit Differentiation that we're going to be using to find the slopes or other applications when we need the derivative for something that's not explicitly a function, and it's not necessarily easy to get it into functional notation. So what I've got an example here is a very ugly problem. I've got x cubed plus y cubed minus 9xy equals 0. And as you can see, this graph that we've got over here is not a function. It does not pass the vertical line test for values of x between 0 and 5. And you can see that the slope for a particular value not only depends on the x value, but also depends on the y value. So what we're going to need is we're going to need a formula where the derivative is actually a function of both x and y. And so that means our derivative is also going to be a relation. And so we're going to need to talk about how do we get that. Now, the tool that we have to do this is the chain rule. And it follows from almost a duh type of relationship. The idea that if I take the derivative with respect to x of y, I get dy dx. Now, I know that seems kind of obvious. It seems like I'm just playing with notation here. But in fact, whenever I take the derivative of something that involves y, I'm going to get my derivative function out of it. And so what I'm going to have to do is determine what my derivative function dy dx is essentially solving for dy dx in terms of x and y. So if this is true, if the derivative of my y function is dy dx, then the derivative of y squared, if I want to deal with this, I basically have f is u squared and u is y. So the derivative of f would be 2u, and the derivative of u would be y prime. So the chain rule tells me that this is going to be 2y dy dx. So whenever I take the derivative of something that involves y, I'm going to end up with this dy dx term, but the derivative is going to be very similar to what I would have had if this was an x. So if I wanted to take the derivative of sine of y, I'm going to treat this as a composition of functions. F is equal to the sine of u, where u equals y. And so the derivative of sine is cosine of u, and the derivative of u would be dy dx. And so I end up with the cosine of y dy dx. So what's important here is using the chain rule means that every time I take the derivative of something that involves y, I'm going to end up with a dy dx parameter that's being multiplied. So I want to go through several examples of this. Let's say that I'm dealing with a circle. Now, obviously, a circle does not pass the vertical line test because I have the values for where y is greater than 0 and the values of where y is less than 0. But I could still look at some particular point and talk about the slope of the tangent line. Notice again that my slope depends not only on the x-coordinate, but also the particular y-coordinate for the point in the relation that we're talking about. So what I'm going to do to take the derivative implicitly, I'm going to take the derivative of every term. So if I wanted to take the derivative of x squared, I'm going to end up with 2x. And if I take the derivative of y squared, I'm going to end up with 2y. And the derivative of a constant is 0. And so I end up with this relationship that 2x plus 2y y prime equals 0. And then at this point, all I need to do is solve for y prime. So I'm going to move the 2x over to the other side. And then divide both sides by 2y. And so what I've got here is that the derivative at a particular point depends on the ratio of the opposite of the x-coordinate and the y-coordinate. So if I was to take a look at what I've got over here, here I have the point negative 3, 4. And so my slope at this point would be the opposite of x over my y coordinate. And at this place where I have negative 3, negative 4, I would have my opposite of x over my y coordinate. And so you see that for the second quadrant point, I should have a positive slope, and I do get a positive derivative. And for the third quadrant point, I should have a negative slope, and I do get a negative derivative. But if I had dealt with this our traditional way, what I would have had to have done was to solve for y in terms of x. I would have had to have gotten y by itself first. So I would have ended up with y squared equals 25 minus x squared. And then taken the derivative, the square root of both sides, which means I've got plus or minus radical 25 minus x squared. And then I would be ready to take the derivative, because my function is really plus or minus 25 minus x squared to the 1/2 power. And so my derivative in this case would be plus or minus 1/2 times 25 minus x squared to the negative 1/2 times the derivative of what's inside times the derivative of u, which in this case is negative 2x. And so I end up with plus or minus negative x over 2 times the square root of 25 minus x squared. Notice I end up with something that's very much more complicated than what I did by the implicit differentiation. But again, if I were to take a look at this, if I'm looking at the point negative 3, 4, I'm looking at this for the opposite of my x coordinate over 2 times the square root of 25 minus my, I forgot my 2 here. So I've got negative 2 times negative 3 over 2 times the square root of 25 minus my x coordinate squared. So I end up with 6 over 2 times the square root of 16, which is 6/8 or 3/4. And notice that I get the exact same slope as before. The only thing that's different is I had to do a lot more work to get that slope. And I run into this questionable, what do I mean by plus or minus? Remember that the positive deals with the top arc of the curve, where y is positive, and the negative deals with the bottom arc of the curve, where y is negative. So this implicit differentiation is a quite useful tool when we're dealing with relations, because it's often more easier just to take the derivative and then solve for y prime than it is to solve for y first and then take the derivative. So let's do a more complicated example, one that we couldn't have done before. So let's take a look at this. I've got 2y equals x squared plus the sine of y. And no amount of algebra tricks is going to allow me to solve for y, because I've got y trapped into the sine function. But I can do implicit differentiation. I know that the derivative of 2 times y would be equal to 2 times the derivative of y. I know the derivative of x squared would be 2x. And I know the derivative of sine of y would, because of the chain rule, would give me cosine of y times y prime. And so what I notice is that I have 2 terms that involve y prime. And since I'm trying to solve for y prime, I want to move all of these terms over to one side of my equation. So I've got 2y prime minus the cosine of y prime equals 2x. And then I can factor out y prime. I'm going to be left with 2 minus the cosine of y equals 2x. And so I end up with y prime equals 2x over 2 minus the cosine of y. And so this is my derivative. And again, I've got my derivative in terms of x and in terms of y. But this is certainly something that's much easier to substitute than if I tried to finagle with square roots and inverse trig functions over here, and then try and take the derivative of this convoluted mess. So the idea of this implicit differentiation allows us to deal with much more complicated relations that we couldn't have touched otherwise, because we couldn't have gotten them in a functional form. Now, in pre-calculus, one of the things that we do is we rotate our conic sections. So remember that having a rotated conic sections means that we have this middle term, this xy term that evolves. So I've got x squared minus xy minus y squared equals 7. And I want to take a look at what's happening at the point negative 1, 2. So if I was to graph this ellipse, this is going to be an ellipse that's tilted almost 45 degrees, and over here at the point negative 1, 2, I want to talk about what's happening. Now, graphically, I should have a positive tangent slope. So I want to take a look at what my slope of my tangent line. As a matter of fact, I want to write an equation for this tangent line. So I'm going to take the derivative of each of these terms. So if I take the derivative of x squared, I end up with 2x. If I take the derivative of this negative y squared, I end up with negative 2y y prime. And if I take the derivative of constant term, I get 0. But this is going to cause an issue here, because what I've really got is I've got a negative x times a y, and so I have to use the product rule. So using the product rule, I'm going to have the first term times the derivative of the second plus the second term times the derivative of the first. And so what I end up with is 2x minus xy prime minus y minus 2y prime equals 0. And as we did before, I'm going to want to collect my y prime terms. I've got two of them over here. And so I want to make sure that these other terms that don't involve y prime get moved to the other side. So I'm going to have negative xy prime and negative 2y y prime remaining. The y will get moved over, becoming a positive y, and the 2x will be moved over, becoming a negative 2x. And then at this point, I can solve for y prime by factoring out the negative x and the minus 2y. And then dividing both sides by that factor will give me y prime equals y minus 2x over negative x minus 2y. And so if I wanted to talk about the slope of the tangent line at this point, I know that my slope is going to be equal to my derivative evaluated at the point negative 1, 2. Remember that because we're doing this implicitly, our derivative is actually the function of two variables, x and y. So I need to know both of these, because just x gives me a different point. So my slope in this case ends up being y 2 minus 2 times x over negative x minus 2 times y. So I end up with 2 plus 2 over 1 minus 4, or 4/3. And so since my slope is this 4/3, my equation of this line is going to be y minus 2 equals 4/3 times x minus a negative 1. And that describes this line here. And I could just as easily talk about the normal line by just flipping this slope and taking the negative reciprocal. So I've got y minus 2 equals negative 3/4 times x minus a negative 1. So the key idea here is anytime that I take the derivative of a term that involves y, I need to end up with a y prime. And the reason we did this example is because of this x times y, I have to treat this as a product rule. So I have to take first times derivative of the second plus second times derivative of the first. If I had a quotient rule, if I had a ratio of something involving y, I'd have to use the quotient rule, and so forth. So, what I want to do is go back to the beginning, back to our old friend here. Our x cubed plus y cubed minus 9xy equals 0. So, taking the derivative of each term, I'm going to end up with 3x squared plus 3y squared y prime minus 9x times y prime plus y times negative 9 equals 0. So I'm just taking the derivative of each term, again remembering that I have a product of two functions here, and so I have to use a product rule. So now I need to solve for y prime, get all my y prime terms together, and I've got 3y squared y prime minus 9xy prime equals 9y minus 3x squared. And then by factoring out our y prime, 3y squared minus 9x is our factor. Then I can solve for y prime, and I end up with 9y minus 3x squared over 3y squared minus 9x. And so this is going to describe our slope. But of course, this depends on our x and y coordinates, so I'm going to have to figure out for which of these points we're dealing with. And you can see that something interesting happens if I try and substitute the origin, because at the origin should have two tangent lines. But of course, substituting 0, 0 in here gives me 0 divided by 0 gives me an indeterminate form. I can't tell what the slope is. And I don't have a common factor other than 3 that will allow me to reduce this fraction to something I could substitute. And in fact, empirically from the graph, we notice that there is no correct answer. One of the answers is going to be a horizontal tangent line with the slope of 0, and one of the answers will be a vertical tangent line with a slope that's undefined. So, the idea behind implicit differentiation is that it gives us a lot more power to deal with relations, and it also allows us to find a simpler closed form for the derivative, although it may involve both x and y, a lot easier than trying to solve for y explicitly for x and then taking the derivative. It's going to save us a lot of time on algebra. It's going to give us a much more friendly answer. And so that's why implicit differentiation is very, very important. In our next lesson, we'll talk about how do we take multiple derivatives using implicit differentiation. So once again, this is Mr. Potter. Thank you for watching. Have a great day.